Let us recall last time what we did was we looked at the first scheme for the equation ut plus aux is equal to 0, right? The first scheme was ujn plus 1 minus ujn divided by delta t plus a over 2h uj plus 1n minus uj minus 1n is equal to 0. And we did the method of lines, and we concluded the matrix A is get 0 the main diagonal, and get 1 here, and negative 1 here. Alright, and you have negative 1 and then 1. And in particular, it is easy to see that A is asymmetric. A transpose is equal to negative A, and then we constructed the eigenvalues are purely imaginary. But the forward Euler stability region is is this disk, okay, centered at negative 1, 0 with radius 1. So the eigenvalues wouldn't be, the eigenvalue times delta t wouldn't be contained in this stability region, and which concludes that the scheme 1 is not stable. The next scheme we'll look at is the Leapfrog that we wrote down, which is it is ujm plus 1 is equal to ujm minus 1, right? And minus, so you are going to do 2 delta t, okay? When you multiply 2 delta t to the right hand side, you get a times 2 delta t over 2h, right? So you have the cancellation, 2 to cancel with the 2, so it's a delta t over h times uj plus 1n minus uj minus 1n. Okay. So for this one, you still have the A is still the same thing, because you still get the spatial discretization is the same. So if you do the method of lines, it end up with the same A. Okay, same A. With same A. So we still have the eigenvalues of A would be purely imaginary. Okay, but of course the ODE solver is not forward Euler anymore. Okay, the ODE solver, so we cannot immediately conclude it is unstable. But the ODE, because the ODE solver is not forward Euler anymore, it is Leapfrog. It is the same guy, right? U and plus y is equal to u m minus 1 plus 2 delta t times f un, right, for the ODE ut is equal to f of u. Okay, we didn't discuss its stability region, but it's a simple exercise. a simple homework problem is that the stability region for this ODE solver is it is actually this line. Okay, it's one here, negative one here along the y-axis. Recall what we do for that from 361 is that we assume f of u is equal to lambda u, right? Lambda u. And then the scheme becomes un plus 1 is equal to un minus 1 plus 2 delta t times un. Mr. That's it, 2 delta t un. I mean lambda, Mr. lambda. So what condition on lambda delta t for un to not blow up? Okay, that's what we meant by calculating stability region, to not blow up when n goes to infinity. So then for the Leapfrog scheme for our advection equation is then whether that's stable becomes the question of whether these eigenvalues is contained in here, right? 1, negative 1. Our last video, in our last video, we concluded that these guys are negative I times A divided by H of sine 2 pi pH. Okay. This is contained in I times B, and here B is less than or equal to 1. Right, that's the same equation, same question. I mean, this guy is times delta t, of course, so its eigenvalues of A times delta t. And which means that because these guys are, because we know these are always its absolute value is always less than or equal to 1. Okay, so that means we need A delta t over H, its absolute value is less than or equal to 1. So we conclude that the Leapfrog scheme for ut plus aux is equal to 0, which is we have uj plus 1 and minus uj m plus 1 minus uj m minus 1 divided by 2 delta t plus a times ux is 2h uj plus 1n minus uj minus 1n is equal to 0. This scheme is stable if a delta t over h is less than or equal to 1. So it the name, the Leapfrog, because it is jumping from j minus 1 to j plus 1 is leaping from j minus 1 to j plus 1, also from m minus 1 to m plus 1, right? So that's where the name is coming from. So we among the 4 schemes we wrote down, we only have 2 left. So the next is a so-called Lax Friedrichs and Lax Wendroff schemes. This LF, this LW. Okay, recall for LF we have we wrote in the form that it was just a fixed first scheme, right? We changed UJN to just the average of UJ plus 1n and UJ minus 1n, and then the rest is the same, a delta t over 2h UJ plus 1n minus UJ minus 1n. So if we rewrite this a little bit, we see that this is just UJN, okay, UJN, and then we need to minus UJN, so what we're going to get plus UJ plus 1n minus 2 UJN, okay, plus UJ minus 1n. Alright, it's easy to see this is the same as this. We're basically adding and subtracting UJN, okay? Minus a delta t over 2h UJ plus 1n minus UJ minus 1n. This way, it is pretty easy to see that we think of this as UJN plus 1 is equal to UJN. It's like for Euler for the ODE. Okay. Minus a delta t over 2h UJ plus 1n minus UJ minus 1n, okay, plus 1/2 UJ plus 1n minus 2 UJN plus UJ minus 1n. So this part is just the scheme to 1, right? And we added the extra term. Added term for Lax Friedrichs, which hopefully would make the unstable scheme stable, we'll see. And by comparison, the Lax Wendroff, we recall that the Lax Wendroff scheme can also be written in a very similar way. UJN plus 1 is UJN minus a delta t over 2h UJ plus 1n minus UJ minus 1n. Again, this whole thing is just like scheme 1, right? What we added in that case was 1/2. If you recall the video before the last video, 1/2 h delta 1/2 delta t squared times a squared h squared. Yeah. UJ plus 1n minus 2 UJN plus UJ minus 1n. Okay. So the difference is at home. Oh, that's 1/2, and this is 1/2 times this. So this is of course the added term for LW if we compare everything with the first simple but unstable scheme. So two things. One is that the matrix A, it was by the way we lost this A 1 over 2 delta t, right? UJ plus 1n minus 2 ujn plus uj minus 1n. So this whole thing should be our big A, right? Big ALF times this long vector, okay? This vector. Right? So what are we adding? We are adding this 1 over 2 delta t of -2, -2, and then we have 1, 1, 1, 1. Right? So same procedure as we did in the last video. Just put Vx to be e to the I 2 pi px, okay, and study eigenvalues of ALF. Simple exercise, or you can read the book. And then basically once we obtain the eigenvalue, we can conclude it's possible for delta t times those eigenvalues to be contained in the forward Euler stability region, which is again this guy. So it is conditionally stable. We're going to do that together with Lax Wendroff in one derivation, which is, so the matrix A for Lax Wendroff now becomes, again, it starts with the same guy for the first skin, A over 2H, right? 0, 0. You have 1, 1, -1, -1. And here -1, 1. And what we're adding, instead of 1 over 2 delta t, we're going to get 1 over 2. We have delta t, and then we have a squared over h squared times this guy. -2, -2, 1, 1, 1, 1. Okay. The second point I'm trying to make here is that we look at the so-called modified equation. If we look at the scheme of Lax Friedrichs, as we wrote out multiple times above, that's just ujn plus 1 minus ujn divided by delta t. Right, this is equal to -a over 2h uj plus 1n minus uj minus 1n. Alright, plus, we're going to rewrite that a little bit as 1/2, that it was 1 over 2 delta t. We're going to get, so this is 1 over 2 delta t here. We're going to multiply h squared and then divide by h squared. Okay, uj plus 1n minus 2 ujn plus uj minus 1n. Okay, for the Lax Wendroff, we're going to do the same thing. Ujn plus 1 minus ujn divided by delta t. This is equal to -a over 2h uj plus 1 minus uj minus 1. Again, that's the same first scheme, and we're adding the fixed term. Okay, we're adding the fixed term. So it was plus 1/2 delta t squared becomes delta t, because we're dividing both sides by delta t, times a squared over h squared. So we're going to get a squared. We already have a over h squared, so we don't need to multiply and divide. But we write the divided by h squared with the other three term, a plus 1n minus 2 ujn plus uj minus 1 n. So this is like the forward Euler discretization of ut, alright? It's equal to, here we have the d0 discretization of ux, alright? The center discretization, plus something, we're going to use that as epsilon times the other term looks very familiar, right? I hope. And that's just a standard discretization of uxx. Okay. So basically, we have we have this is that, and then we have this guy is that guy, right? And we have this guy is that guy. Okay, so the difference between the two schemes is that this epsilon, right? The two epsilons are different. So these two schemes are actually, they are, instead of solving this advection equation ut is equal to negative aux, we solve ut is equal to negative aux plus epsilon times uxx. This so-called modified equation. The scheme is actually closer to a different equation. The equation is called the modified equation, and this epsilon uxx is like Laplacian. It's like small additional Laplacian. This is also called artificial viscosity, having some diffusion. In other words, viscosity is a scheme. It's a stabilized things. Diffusion, things diffuse and gets more stable. Okay. So the amount of viscosity epsilon LF is just 1/2 h squared over delta t. The amount of viscosity for Lax Wendroff is 1/2 a squared delta t. So the matrix A for the Lax Wendroff and Lax Friedrichs now is just negative A over 2h. We have 0, 0, 1, 1, negative 1, negative 1, negative 1 here, 1 here. We're adding this, so we're going to get epsilon over h squared, alright, of this matrix, negative 2, negative 2, 1, 1, 1, 1, depending on the particular epsilon, right, with epsilon being 1/2 h squared over delta t for Lax Wendroff, Lax Friedrichs, and epsilon being 1/2 a squared delta t for Lax Wendroff, right? So this part is just a ux, a negative aux. This part is epsilon uxx, okay? So we're going to derive the eigenvalues of this matrix in detail in the next video, next lecture. However, one more thing I want to point out now is that if this turns out to be the same as a Leapfrog, the condition, if we have the a delta t over h is less than 1, okay, less than 1, and we want to get some sense of how much viscosity this epsilon LF versus epsilon LW, how much viscosity is each of these schemes adding to the equation, To figure that out, we just simply, if you divide Lax Wendroff epsilon, Lax Wendroff divided by epsilon Lax Friedrichs, we see which is 1/2 a squared delta t divided by 1/2 h squared over delta t. What's that? That's just a squared, alright, delta t squared divided by h squared. So this becomes a delta t over h. You see this ratio comes up a lot. This whole thing squared. Alright. So if a delta t over h absolute value is less than 1, this square is also less than 1. Which means this means epsilon LW is less than epsilon LF if a delta t over h is less than 1. In other words, i.e. Lax Wendroff adds less viscosity, which means that Lax Wendroff is less dissipative. The more viscosity you add, it's like the stronger diffusion you are introducing. Diffuse means it's dissipative. The things dissipate, diffuses. So the less viscosity means the less diffusion, less dissipative. Alright.